Hello, in this video I'm going to talk about the convolutional neural networks, which will be a very brief introduction and some mathematics behind how backpropagation works. At the beginning, as an inspiration to why we're talking about convolutional neural networks, I'm going to show a clip about this, where this method has been used in real life applications. And I'm sure there are many more applications, but this is just one of my favorite, using deep learning in automotive vehicles. Okay, so as you can see, this video is by the NVIDIA company, where they, at the beginning, as you can see, the vehicle is not very good in driving automatically, but then after 3,000 miles of training and learning, then it improves. The whole idea behind this field of deep learning or convolutional neural networks, which is the backbone of deep learning, is that scientists wanted to mimic the human's vision and brain. So how the vision, human vision system works and how the brain works. Of course, we cannot exactly copy paste this, but we try to mimic that. So if I give you a photo of a cat like this one, and I ask you, okay, what is this photo? You say it's a cat. Why is that? Because you have already seen a photo of a cat. You know what a cat looks like. That's why in your brain you straight away know. So this information is in your brains. It's been saved somewhere. That's why you know. If I give you another photo whereby the full information is not there, you somehow know that, okay, this might be a cat or a leopard or something. Why? Because you can see some sort of abstraction. You say, okay, this is an eye, this is an eye, and the texture distribution and so on. Okay, so, and this is the human ability of abstraction, which is a very powerful concept. But if I show you an image like this one and I ask you, what is this? Unless you are Chinese, you don't know what that is. So this is number 4 written in Chinese, right? If you don't know, it means that you have never seen this image before. You don't have this knowledge saved in your brain somewhere, right? And by mimicking this idea or this approach, I mean that the ability of learn. So it's like a child. When you show the child a picture of a cat, like once or twice or 3 or 4 times, then he or she will gradually learn. The next time, even if it is like after a week or after months or years, you show another picture of cat, they will recognize it straight away, because they have stored information about how a cat looks like, so on and so forth. And the other inspiration was about the human brain neurons and the structure of these neurons and how they communicate, how the information flows from one neuron to another, was another inspiration to introduce the convolutional neural networks. And the nature of the communication between the neurons in our brain, as I said, is what the scientists behind proposing the very early ideas of convolutional neural networks were claiming that, okay, we somehow see that there's a hierarchical way of passing the information between the neurons in our brain. And it is this way that we try to design a hierarchical way of extracting features, which means discriminative information from the input of our systems, right? Now, if I want to describe the convolutional neural networks, like any other classical recognition system, it consists of 3 stages. First, your input, what is your input? And second stage is the feature extraction, which is this dashed red box. And then the final stage is the classification. So first you need to have some data where you want to classify. Then you extract features, i.e. discriminative information from the input. And then you have a classification stage where based on the features you extracted, you want to classify whether this image belongs to this category or this class or the other class. And I'm going to describe this or discuss this briefly. So the main components of convolutional neural networks are input data, feature extraction, and classification stage. The input data can be an image, a voice, a text, a sequence of numbers, and so on. The feature extraction stage, the main ingredient in the feature extraction stage is the filters, which can be in different sizes. And sometimes this filter is called kernels, or some people call them weights. The classification stage, mainly in convolutional neural networks, are neural network, which is the classifier, but it can be other classifiers, things like random forest, k-nearest neighbor, support vector machine, and others. How do you extract features, okay, in the convolutional neural networks? So the main idea here is the idea of a convolution, right? And let's assume that the input of my system is a matrix like this. And by the way, I'm going to be using image as my input. An image mathematically is just a matrix of numbers distributed and arranged in some way, whereby humans, they can see them as there's an edge and there's an eye and so on. I'm not going to go into the details of how to represent an image mathematically, but it is enough for you to imagine that an image is just a matrix of numbers that we have, and a computer can read this and understand it. So I need to have a filter and a kernel, and I'm going to convolve this filter with the image that I have, and I will extract features, or they call them feature maps. How do we do that? So the previous filter that I have, if I want to convolve it with the input, then what do I do? Convolution is an element-wise multiplication, whereby you multiply each element in your convolution filter by its corresponding position in your input. So first, you multiply it by the top left corner, and I have a 3 by 3. So when you multiply this, just as I said, an element-wise multiplication, 1 multiplied by 1. So here it gives you 1, 0, 1, 0, 1, 0, and so on. And then you add them all, and it's 4, because you have 1, 2, 3, 4, and the rest is 0. Okay. And you do this for the rest of your image, or for the rest of your matrix. And these are the numbers, and these are the features that tells you, okay, this is how the numbers distributed or arranged in this matrix. And this is our feature map. And it is the same thing when you have an image comes to your system, you do exactly the same thing, and you get a feature map. Now, the previous example was a one channel. We know that an RGB image, a colored image, constitutes of 3 channels, red, green, and blue. And it's the combination of these 3 that gives you different colors. So for that, you do exactly the same thing, but instead of 1 channel, you have 3 channels. Then you will have 3 filters, and you multiply each filter by its corresponding channel, and you do the convolution, and you store the numbers here, which is in your feature map or your output. So At each multiplication stage here, you get a number. You add this with the second channel, which is the green, and you add this with the result you get for the third channel, plus a bias, and you get a final number, and you put this number here. So I hope this is clear. Now I'm going to talk about the bias. What is this parameter here? What is this bias? Is this really important? What happens if I'm not using the bias? So bias. In small networks, bias value allows you to shift or move the activation function. And this can be critical for successful learning. I should have said this in the beginning that one thing that is differentiating convolutional neural networks with other classical recognition systems or feature extraction techniques is the ability of learning. So in convolutional neural networks, you have the ability of learn, i.e. to modify the way you extract features. And this bias, if your network is small, and by small, what do I mean by small? So there are many ways to define small networks. Small networks might be the number of parameters or hyperparameters that you have, or the number of layers that you have in your convolutional stage, and so on. However, if your network is large, resource is saying that removing bias makes almost no difference. So whether you have a bias or not, it will not make much of a difference in your final result. Now, mathematically, if you want to imagine the effect of bias on your system, it's like thinking about this constant parameter here if you have a linear function, okay? So a linear function is y is equal to ax plus b. Now, if I have this equation and I want to graph this equation, okay, this parameter b allows you to move the line up and down to fit the prediction with the data that you have, okay? So what do I mean by this? So if I have a point cloud, a small point cloud like this, and I want to fit the line that I will get using this equation to fit this data, to approximate this point cloud in a good way, this parameter b will give you the ability to predict this better. How? So at the beginning, imagine you don't have this parameter b. If you want to graph y is equal to ax, now you may get a line like this, or a line like that, or a line like this one. No matter how hard you try, the lines that you are getting, these lines, all of them will go through the origin. And this parameter a will control it, okay? And none of these lines is a good approximation for the point clouds that you have, or for the point cloud that you have here. Now, of course, in practice, you may not have like 10 or 15 points like this. You may have thousands and thousands of points. And instead of, you want to represent these point cloud with a line that approximately represent your data. What happens if I have B? Now, you may have a line like this. You may get a line like that. And this is this parameter B that controls where is this line draws. You may get a line like that or a line like this one. And you see, okay, this one is a better approximation in comparison with the other three lines that I have. So the effect of bias, or the role of the bias in your networks can be thought in this manner. And it is critical to remember that if you have a small convolutional neural networks or a small CNN, then the effect of bias would be more clear. And as I said, it is critical for successful learning. So it helps you to learn better. Now, this is in a 2D. If you're on an X and Y plane, what happens if you are in 3D or in a higher dimensional stage? Then the effect of bias can be demonstrated as follows, as you can see here. So if you have this point cloud in a 3D, and this the same point cloud here, now the top graph, you don't have a bias. The bottom one, you have a bias, and you can see the bias helps you to estimate or to fit the plane better in comparison with the top one, with the top graph where you don't have a bias. Okay, now so remember we are still in the convolutional stage. Another parameter that you need to know is padding, and padding is nothing than adding rows and columns of 0 to your data, to your input data. And why is that? If you want to get the convolved image or the convolved feature map to have the same size as your input, then you add padding. And it is known as, if you put same as a padding, it means that after you multiply this kernel with the input, you want the size of your feature map or your convolved input to have the same size. Okay, so this is a 5 by 5 and this is a 5 by 5. Why? Because I have added this padding, and this is what you get. So remember, so convolution is an element-wise multiplication, and you add up all the elements in your window, and you get these numbers. And you see, because I have added the padding, then the results of the convolved feature map is the same as my input. And remember, the stride here is equal to 1. So next I'm going to talk about the stride. So stride, so you can have stride of 1 or 2. So what is it? And so stride simply is the number of pixels a convolutional filter is moving along X and Y coordinate. The main idea behind using this stride is to basically reduce the dimensionality of your input data. So if I have my image like this is the filter that I will be convolving at that position, let's say. Now the next stage, if the stride is equal to 1, you shift this filter to get the second convolution from the same image, or the second convolution process, by 1 column. Okay, so once stride is equal to 1, so you move 1 column to the right. So once you finished this, then you move this by 1 row down again. So it is 1 row and 1 column down and right. If stride is equal to 2, you just push this next stage by 2 columns, and so on. Now, what do we get when we apply convolution to my input image? So say that I have applied convolution onto this image. Say I have 9 filters, and the size of my filters are 3 by 3, and the stride is 2 by 2. The feature maps you get looks something like that. Okay, and you see that at different filters extract different information from the input image. One thing I should mention that in practice, these filters are not random numbers, or not any numbers that you bring. Well, I suppose you can take random numbers, but you will not get good results. But these filters, they are sampled from a Gaussian distribution. So the numbers from the filters that we have at the beginning will be sampled from a Gaussian distribution. Another concept we have in convolutional neural networks, or in CNNs, is known as an activation function. And one of the famous ones is known as RELU. RELU technically or simply is a function, a function such as f of x, which is equal to the maximum of 0 and the x. So whatever number you give to that function, it takes the maximum between the 0 and the number that you have. Okay, which means that if the input of that function is a negative number, it returns 0. If it is a positive number, then it returns the number itself. In other words, the convolved images or the convolved filters that you've seen before, whenever you have a negative number, this RELU, applying the RELU onto each element here, will convert this into a positive number. And instead of the negative numbers here, you will get a 0. So f of 1 is 1, f of 14 is 14, f of minus 9 is a 0, f of minus 20 is 0, f of minus 2 is 0, and so on. Okay. Now, so based on some of the resources that I have read, they're claiming that a RELU greatly accelerate the convergence of stochastic gradient descent compared to the sigmoid and tan hyperbolic functions. So I do not want to go into the details of this discussion, but what the convergence of stochastic gradient descent means here is you are learning better and quicker, okay, using the RELU function inside your convolutional neural networks. That's what they claim. Or you learn faster. Now, of course, RELU can be implemented simply in comparison with other activation functions like a sigmoid or tan hyperbolic. Now, of course, some of the resources saying that RELU units can sometimes be fragile during the training and can die. So what does this mean? In another word, it means that a large gradient flowing through a RELU neuron could cause the weights to update in such a way that the neurons will never activate on any data point again. Okay. Now, if I want to have a visualization of what does a RELU do to my input after I apply the convolution. So imagine you have an image like this, which is number 4 here, and you multiply it with the kernel that you have or with the filter. You do your convolution, you get an output like this one. Applying a RELU will result in getting a result like this one. So you see the smoothness and the gray areas will be reduced, which are the results of having a negative numbers in your convolved output. Okay, so another concept you have in convolutional neural networks is known as a pooling or dimensionality reduction. Pooling layer is responsible for reducing the spatial size of your convolved feature. Imagine if you are inputting an image of a size, let's say 500 by 500 to your system. Now you want to get the dimensionality of this image sooner than later, okay? And how do you do that, reducing this dimensionality? They are proposing a pooling. So the two popular pooling processes are known as a max pooling and average pooling. Max pooling, so if you assume that, okay, I want to take a 2 by 2 max pooling, so you take a window of 2 by 2 from your convolved feature map, and you take the maximum number from this 2 by 2 window, okay? So as you can see, so the maximum number here is 7, the maximum number here is 9, the maximum number here is 8, and the maximum number here is 5. Maybe you're saying, no, I'm going to take a 2 by 2 average pooling, then instead of a max pooling, you take the average of this small 2 by 2 window, and you put the resulting value here, okay? Now, so this is the pooling. And another step that you have, or another process you have in the feature extraction stage of the convolutional neural networks is known as a flattening. So flattening is what? If you have a matrix like this, you just flatten this out, and i.e. you make them as, you represent this as one column. Now, of course, in convolutional neural networks, you may have layers, so more than one layer, so more than one matrix stacked. So you flatten the first layer here, let's say it gets you all the way here, and then you flat the next one, and then you concatenate it with the first one all the way here, all the way there, and so on. So sometimes you get thousands of numbers in this flattened feature map. Now, if I want to put everything together in the feature extraction stage of CNNs, so you have an input data, and then you apply your convolution, say with the stride 1 and RELU, you get a number of feature maps or representations of your input image like that. And these numbers, depending on how many filters you have chosen to convolve your input by. After you have this one, as we mentioned, you apply dimensionality reduction, which is known as a pooling. Say you decided to apply max pooling. So what you get, so the dimensionality, i.e. the number of rows and the columns of this convolved feature maps here is the same as your input. You apply max pooling. Say if this is a 100 by 100, this is again 100 by 100. Say you applied max pooling to be a 2 by 2, then this gets you to a 50 by 50. So you reduce the dimension by half. And say you decided you want to apply another convolution with a stride 1 and RELU, and then you want to reduce this dimensionality further. So you get a 25 by 25, for example, and say, okay, this is enough. I want to flatten my feature maps and I want to feed it to a classifier. Then what you do, you apply the flattening, and you see, you flatten the first layer, and then you flatten the second layer and the third layer, and then you put everything together in one column. And this is your flattened feature map, or your flattened features, or these are the features that you have, okay? Now, these are the building blocks, or a very quick introduction into some of the important concepts that you should be aware or you to know inside the convolutional neural networks. The next stage is known as a classification. As I said, the main classification method inside convolutional neural networks is known as a neural network. And I'm going to briefly discuss that. How is it and how can we apply it? So convolutional neural networks is something like this, as you can see. So this is the input layer. So remember, when I flattened my layers of the feature maps, so these are the numbers. So these numbers will be fed into my neural network. So this is the input layer, which is coming from the flattening. Now, for simplicity, say you have 3 numbers here, and you decide to generate some hidden layers. So these are neurons, and each neuron will be connected to every single neuron in the second in the layers that are coming afterwards. And finally, you have an output layer. Now, of course, things are not simple. So this is if you have 3 numbers. What happens if you have 6 numbers or 7 numbers, and you decided to have, say, 10, 15 neurons in your hidden layers? And as I said, because every single number here needs to be connected to all the numbers that are coming afterwards, okay? And the same thing for this guy and this one and this one. You see, this is a very complicated and crowded network here. And once I have my final decision here in the neural networks, I want to update these numbers, which are called weights here. I want to update it so that I reduce the errors, reduce the amount of errors that I have. So the inputs are coming, okay? You calculate your final prediction scores, and then you backpropagate the error because you have some errors. Hopefully you don't have a lot, but the errors that you have will be backpropagated to all of these numbers here, all the way through these input numbers and to the convolutional layers. And then you do your training again. Once you have the errors, you backpropagate the errors back and forth until you reduce the errors as much as possible. Now the question is, what is this process and how do you backpropagate the errors? Okay, let us start with a very simple neural network and see how it works. So imagine in your input layer, you have two numbers, x1 and x2. And you decided that, okay, for simplicity, I want to have one hidden layer, which constitute of two numbers only, h1 and h2. I beg your pardon, this needs to be h2. Let me correct this. Yep. And x1 will be connected to h1 and h2. x2 will be connected to h1 and h2. Then you have your output layer, which is y1 and y2. And again, this neuron here, or this number here, will be connected to this 2, and this one into that 2 as well. Now, of course, we said you have bias because you have two connections here. So you will have two biases here. So the first one, let's say this is B1 and B2, and the bias will be connected to H1 and H2, and bias 2 will be connected to Y1 and Y2. And what are these connections? So these connections are simply weights that you generate from scratch. Again, these weights, the majority of the systems will generate those weights based on Gaussian distribution, as I said. And then these are the weights. So these connections are numbers that you generate and they follow a Gaussian distribution. And these biases are 0 or 1, or it could be any number depending on how you want to fine tune your system. Okay, so if I have two numbers here, how am I going to send these numbers, send this number, let's say, through this network to this 2 node here, and from this 2 node into this 2 node, into the final layer, or into the output layer. So first of all, we have H1 star, which is known, which can be defined as a W1. So H1 star here is equal to W1, weight number 1 multiplied by X1 plus weight number 2 multiplied by X number 2 plus B1. And what is the activation function here? So you have a sigmoid function, and a sigmoid function can be defined as f of x is equal to 1 over 1 plus e to the power minus x. And what is h1? Then h1 is equal to 1 over 1 plus e to the power minus h1 star. Okay. And similarly, h2 will follow the same idea. And of course, y1 is the same thing here. Now here, instead of defining these separately, I just put it in one equation. Okay. Now, yeah, so this is H1 and this is H2. Now let's start by defining or giving some numbers so that you actually know that how am I going to do this calculation. So assume that X1 and X2 are having those two numbers here, 0.05 and 0.1 or 0.10. Now randomly generate the weights that you have. Okay, so these are the weights that we have, weight W1, W2, W3, all the way to W8. And you generate your biases to be this two number, an 0.35 and 0.60. Okay. So these are the numbers. that we have generated from scratch. Now, how am I going to calculate H1 and H2? So let's start step by step. So I have X1 and X2, I have W1 and W2. So this is the activation. At the beginning, I will have H1 star, and then once I have the H1 star, the activation function will give me the value of H1. And I have a bias as well. And these are the numbers that I have that I have generated. So calculate H1 star. So H1 star is equal to what? I have W1, which is an 0.15, is this number, multiplied by X1. X1 is given, is 0.05, plus W2, X2. I have defined W2, and this is X2. Multiply these two numbers, plus bias 1, B1, is 0.35 and 0.35 here. You do this multiplication and summation, you get an 0.3775. This is the value of H1 star. Now H1 star needs to go through the activation to give you the value of H1. So what is the activation as we have defined in the previous slide? So H1 is equal to 1 divided by 1 plus e to the power minus H1 star. What is the value of H1 star? We have calculated it is this number. So you just, instead of H1 star, you substitute that number, you do your calculation and division, you get this number. And this is the value of H1. You do exactly the same thing, okay? W3 and W4 is given, W3 and W4 is given. Again, X1 and X2 is given. Bias 1 is given, okay? You follow the same strategy and you get an 0.59688 for H2. Now, if I want to calculate from H1, if I want to calculate Y1, okay, what do I do? So H1, I have calculated it. It is this number. W5 and W6 is given. W5 and W6 is given. B2 is given. Okay, you substitute these numbers in this equation. So Y1 is equal to what? 1 over 1 plus e to the power minus of H1 star, H1 multiplied by W5 plus H2 multiplied by W6 plus B2. Once you do this calculation, then you calculate the activation, use the sigmoid, and it gives you this number. Y2 is the same thing. You have H2, and for the Y2, so H2 is given, H1 is given, W7 and W8 is given, and you do your calculation and you get this number. Okay, so this is the full equation, and this is the number substituted, and this is your result. Okay, now, so this is my output layer. So the features that I have extracted, or the input layer, going through this process, it gives me two outputs, Y1 and Y2. Okay, now in practice, on reality, these two numbers, I need to compare it with what I have, or what is the actual label, okay? Or what is my target? So because I have two outputs here, it means that I have two labels, or I have two targets. Let's assume that the first target is equal to an 0.01 and the second target is equal to an 0.99. How do I know what is the amount of the error that I have made? So it is simply, so the total error can be calculated following this equation. Or you can simply say total error is equal to the error that you have in Y1 plus the error that you have in Y2. You just add them all. And error in Y1 is equal to what? 1 divided by 2 of T1 minus Y1 to the power 2 plus half of T2 minus Y2 squared. Okay. Because I have calculated Y1 and Y2, and I have the actual labels, or my target is T1 and T2, which is these two numbers. So you just substitute the numbers that you have in this equation, and you get your total error that you have from this prediction, from this process. And the error is in 0.2983, okay? Now I want to reduce this error. How do I do that? Okay, now you know what is the amount of the error that you have in your system. You want to backpropagate this error through the layers, through the weights that you have, and you want to fine tune it in such a way that you reduce this error as much as possible, because that is the aim. Okay, so let's start by updating weight number 5, because this is, let's say if you have to start somewhere here. Let's assume that I want to update weight number 5. How do you update that one? So updating weight number 5 here is equal to what? Weight 5 minus eta multiplied by partial E total divided by partial W5. Now, what is eta here? Eta is something new coming to the screen. So eta is an optional learning rate, say an 0.5. Again, this is another parameter that you the user needs to define it. And what is this ratio here? And this ratio is the gradient with respect to W5. This is what is known as a gradient descent, or simply just mathematically I call it a gradient. So this is the gradient with respect to W5. Now, what do we want? We want to know how much a change in this weight, in this specific weight here, will affect my total error. In other words, I want to know the change that I make in W5 and its effect to my final error. Okay, so mathematically, this can be measured using a partial derivatives or gradient with respect to W5. And now I want to mention that we are teaching undergraduate mathematics students, or sometimes even in GCSEs or A-levels, we teach them partial derivatives. And this partial derivative here simply is this concept with some complications, I should say. So I want to calculate the partial E total of a partial W5. So how do I do that? In mathematics, we have, and in calculus, we have something known as a chain rule when it comes to partial derivatives. So partial E, partial W5 is equal to what? Partial E, partial Y1, multiplied by partial Y1 over partial Y1 star, multiplied by partial Y1 star, partial W5. Okay, so this is a chain rule, straightforward. Now, what is E total? This was the equation for the E total that you have seen before. So I want to backpropagate this into Y1. So using E total Y1, I will calculate this one. And using Y1 star, I will calculate this ratio here. And using Y1 star W5, I will calculate this one. So if you think that, okay, how do I know, or where is this terms coming from? So you see, I have W5 and I was in the E total. What is my total error? So the total error was here. In order to get to W5, you have to backpropagate this error into Y1, and from Y1 to Y1 star, and from Y1 star into W5. And this concept is modeled as, or put together using this chain rule in calculus. Okay, now let's calculate the first ratio. So the first ratio, partial E total partial Y1, is equal to what? It means that I will take partial Y1 This is how you take the derivative or partial derivative here. What is E? So instead of E, you put this equation. This is the equation, and you do your derivative, okay? So you do your derivative with respect to y1. Doing this derivative with respect to y1 will result in this, and substitute the numbers that you have here, which is given before, you get this number. So you fine tune, sorry, before you go to fine tune, this is the ratio of partial E of a partial y1. Let's calculate partial y1 of a partial y1 star. So to do this calculation, before I go into the numbers, partial y1 over partial y1 star is equal to what? Is equal to y1 multiplied by 1 minus y1. Why is this? If you're thinking, okay, where is this coming from? Now, here is the mathematical derivation of that. So I know y1 is my sigmoid function. Okay, so y1 mathematically is equal to this function. And if I want to find the derivative of this function, this is how you do your derivative. Okay, and I don't want to go through the details, but this is every step that you follow. And at the end, you get what? y1 multiplied by 1 minus y1. Okay. And what is y1? The value of y1 is given, or we have found it in the previous slide. So you substitute the number here, 1 minus the number that you have for y1, and you get this number. Finally, what is the value of partial y1 star with respect to partial w5? Again, what is y1 star? You just put the equation of y1 star, which is this equation, we have defined it before, and you find the partial derivative of this equation with respect to w5, which is equal to h1. Why? Because partial derivative of this one will be 0, this would be 0, and this is the only one that I have w5 as a variable, and this would be 1 multiplied by h1 gives you h1. And what is the value of h1? We have calculated it in the previous slides, and this is the number. Now I have the three ratios that I wanted to. You put those together and you multiply them. So this is partial E partial y1, it's that number, multiplied by an 0.1868, which was this ratio, multiplied by the result of this ratio, and you get an 0.0821. Okay, now this is what? Partial E partial W5. Now, how to update W5, weight number 5. We said this is the equation. You have weight number 5, you have defined it, or you randomly generated this one, minus what is your learning rate or your eta value. Your eta we said we defined as 0.5. What is partial E partial W5? It was this number that we have calculated it. So you do your calculation here, it gives you an 0.3589. So this is the new or the updated value of W5. Okay, so you fine tune or you update your W5 from 0.4 into this new number. Now you follow the same strategy to update W6, W7, and W8. Okay, and these are the calculations that I have did. I hope I was doing everything correctly, but you can double check and let me know if I have made any mistakes. Now, what is the mathematical formula for updating the weight in W1? Okay, why? Because now I have updated all the weights that I have here. Now I want to update this guy, right? Which is in the previous layer. Okay. So remember what we need. So I have total error, i.e. error in Y1 and error in Y2. So this should have been E2 or E of Y2. You backpropagate this into H1, and from H1 to H1 star, and from H1 star into W1. And the same thing from this guy, okay? So partial E total, partial W1, if I want to do this calculation, this is the chain rule. Now the chain rule here, again, so you have two totals, remember? Partial E total, partial W1 is equal to what? Partial E total with respect to H1 multiplied by partial H1 over partial H1 star multiplied by partial H1 star partial W1. Now, how do you calculate this one? Partial E, partial H1. This is how you calculate it. Partial partial E with respect to Y1, partial H1 plus partial E with respect to Y2 over partial H1. So you add the errors that you have from Y1 and Y2 from the two outputs that you have. Now, again, so remember, we are still in this trying to figure out how to calculate this ratio here. So this ratio can be calculated using this formula. Now, in this formula, how do I calculate the first ratio, which is partial E, partial H1? This is how you calculate partial E, partial H1, which is equal to this two ratio multiplied by each other. And how do you calculate partial E1, partial Y1 star? Okay, it is equal to these two numbers, or these two ratios. Now, partial E with respect to Y1, partial Y1 is equal to this number. I have calculated it before. And what is partial Y1 star is equal to this number. We have calculated in the previous slide. You do this multiplication, you get this number here. Now, what is partial Y1 star, partial H1? Okay. Now, I claim that this is equal to weight number 5, and this is equal to 0.5. I leave this as an exercise for you. And what is partial E1, E of Y1 over partial H1? Well, it is simply equal to an 0.1385. We have calculated it here, multiplied by this guy here. Okay. So remember, from this, we focus on this formula. And from that, you go into this formula, and then this formula, and then this one. So similarly, if I want to calculate partial E sub Y2, partial H1, okay? So now this calculation here was for this term. How do you do this calculation? You follow the same strategy and you get this number, okay? Now finally, what is partial E total with respect to partial H1, i.e. this ratio here? So we have calculated this one, it is equal to that number. And the value of this one is equal to this number. You plug them here and you get this. So this is partial E total, partial H1, which is this ratio. Now I want to calculate this one and that one, these two ratios. And I guess this should be straightforward for you. And then once you have this two number, okay, you will update W1, okay? And so on, you update W2, W3, and W4 here, okay? Now, so then how do you update the biases? How do you update the weights in the convolutional layer, okay? I'm going to stop here, and hopefully in the next videos, I will summarize what I've talked about the backpropagation of the errors, and I will discuss the updating of the weights in the convolutional layer. Thank you for listening.